we looked on the last class how we can draw Lewis structures, how atoms are bonded together, and we talked about two different bonding models. Well, the Lewis bonding theory leads to showing us how we can bond ionic compounds and how we can bond covalent compounds. We touched briefly on ionic compounds, and we said that they completely transfer electrons from one atom to the other during the bonding process. But the rest of the lecture we spent on looking at molecular compounds. And molecular compounds are those which share electrons or bond through electron sharing. So we, at the very end of the class, we did to talk about electronegativity and bonds, polarity, polar bonds, and so we go from something that is a pure covalent bond where the electrons are shared equally to something that is a polar covalent bond where the electrons are shared unequally to all the way over to a pure ionic bond where the electrons one is transferred to the other, and they're two completely separate atoms just sitting next to each other by attraction force. So the last thing we did is we went in and we established our rules for drawing Lewis structures, for predicting the connectivity of the atoms. How are the atoms connected together? And so we looked at a couple of examples of molecules that bond with single bonds. So today what I want to do is show us, we'll start looking at a strategy. The first thing we're going to do is look at how we form double bonds. So we're going to do two different types of examples today. Two are going to be ions, polyatomic ions, how we draw the Lewis structure for polyatomic ions, and a few are going to be how we would draw Lewis structures for molecules that form more than one bond. So the first example we're going to look at is going to be carbon monoxide. So our rules say the first thing we do is connect the atoms, put the least electronegative atom in the middle. There's no middle here. Then we look at the number of valence electrons that each one brings. Carbon, there's one atom of carbon, and it brings how many valence electrons? 4. The oxygen, there's one oxygen atom, and it brings 6 valence electrons. So the total number of electrons that we have for bonding is 10. So then we said the next thing that we do is we look at the number of electrons that are already used up in the formation of the bond between the two atoms. In this case, every dash, remember, in a bond represents 2 electrons, right? So there's one bond, so therefore we can say that 2 electrons have already been used up. So therefore there are 8 electrons to go around. So we say that we start putting electrons around the terminal atoms, and we put them around the most electronegative atom first. Oxygen is further to the right on the periodic table, so it's more electronegative than carbon. So we're going to start putting our atoms first, or electrons first on oxygen. We can put 6 there, and then that gives us 2 more to put on the carbon. Let's see. So now when we evaluate it, we look and see if carbon, we want to see, make sure every atom has a complete octet around it. So does carbon have a complete octet? No, it's unhappy. It does not have the 8 electrons it needs to have a complete octet. What about oxygen? Oxygen is happy. Oxygen is fine. So what we now need to do is figure out how we can rearrange the electrons to where we can share them between the two atoms to where we can make both sides happy. So what we would do is the first thing we would try is to move one of these pairs of electrons to form a bond with it. So When we do that, we end up with this. So now let's reevaluate. Is carbon happy? No, it's still not happy. Oxygen is still good. So therefore, we're going to have to now move another pair of these electrons. And so what we're going to end up with now is a triple bond. So now, looking at carbon, it has 2, 4, 6, 8. It has 8 electrons, so it's finally happy. Oxygen has 2, 4, 6, 8 electrons, so it's finally happy. So we have to move electrons to form shared pairs until we can satisfy every atom with a complete octet. And of course, if we're talking about hydrogen, we're forming duets, but hydrogen never does multiple bonds, only single bonds for hydrogen. Mm-hmm. That means that it has 8 um, electrons around it. So let's see how we count these. This is 2, that's 2 electrons. Each Y represents 2. So this is 4 total. So therefore, around carbon, in this case, there's not an octet. Octet, 8 electrons. Okay, so it only has 6. So it's not happy. Okay, all right. So let's look at one more. That's how we form the multiple bonds. We're going to have a couple of examples in a second. Now let's look at ones that are polyatomic ions. What do we remember about polyatomic ions? The first. Oh no, that was just that was a multiple bond. So basically, it's a neutral molecule. So we were just basically drawing a structure for a neutral molecule, and it happened to be that the structure required us to draw multiple bonds. Neutral means there's no charge. Polyatomic ion means it has more than one atom, and the overall molecule is an ion. It has a charge, not neutral. Yes. The random bond. Okay, you each time you evaluate, every time you like we started at the top here. I'm sorry, I've been doing lectures all night on the thing, and my voice is going. Um, but every time you start with the potential structure, for instance, this is our first potential structure here. We have all of the electrons that we have between both atoms. We have all the electrons distributed. Now we need to look at each atom separately and count the number of electrons that we can say are shared by it. So there's 2 here and there's 2 here. So here there's only 4. So therefore that's not enough electrons to make this a stable molecule. It has to have 8. So since it has to have 8, then we know that we need to take a pair that's shared on another atom and move it. So when we do that, it has to have 8 because every atom in every bond arrangement would like to look like a noble gas. So we're always trying to achieve 8 electrons around any element in a bond, except for hydrogen. Hydrogen wants to have 2. And sometimes we have a couple more exceptions we're going to talk about in a few minutes. Lithium, beryllium, and boron can have less. But the ideal configuration, what every atom strives to do, is to have 8 electrons around it. And so that's why we have to do this sharing. And when we talk about ionic compounds, that's why we transfer electrons to where the outer shell has 8. In every transaction, we're trying to achieve 8 for all compounds except for hydrogen, where we're trying to achieve 2. Okay, so looking at a little structure for hydrochloride ion. It is a polyatomic. It's got more than one atom. That's the hypochlorite ion. Polyatomic one. It's got 2 different kinds of atoms. So when we draw a Lewis structure for it, the first thing we need to do is draw a skeleton structure. Put the least um, electronegative in the middle. In this case, um, I'll show you why that won't work. Mm-hmm. This is the hypo. Remember from general chemistry, that's what the ion's name. So this is not the strategy that we're taking. This is the name of the ion. Okay, so we just like carbon monoxide with CO, when we drew a Lewis structure for it, this is a hypochlorite ion. Okay. All right. So anytime you have an ion like this, the overall, the whole thing is charged. So we put it in brackets. Okay. So the first rule, which tells us to, if for chlorine, we have one of those, it brings 7 valence electrons. For oxygen, we have 3 of those, it brings 6 valence electrons. But now we also have to account for the charge. It has an extra electron or a negative charge. Let me write negative charge. Okay, so therefore we have 26 electrons total. 6 of them have already been used up in bond. So therefore we have 20 electrons to distribute. And it just so happens so now when we evaluate each one of these, oxygen is happy. I'm just going to draw a check mark instead of a smiley face. Chlorine has 8 electrons. 2, 4, 6, 8. It's happy. This oxygen is happy. And so is this oxygen. Because if we didn't, we could misrepresent that there's a negative charge on one atom or the other, when we're actually saying that the entire molecule is charged, the whole thing. So we basically are saying over the distribution of all these electrons, there is a net negative charge over the whole molecule. There's several of them. We have many different anions or cations. Remember your polyatomic ions. You have different variations. You got chlorate, perchlorate, phosphate, etc. Track 6. Okay, so when you draw your skeleton, you've used up 2 electrons in between each atom when you make your bond. So those are taken out of the equation because we've already used those, and they can't be available to distribute around the atoms. Mm-hmm. They're not going to do that to you this time. um, but when it was in general, we were responsible for naming your ions. but it's not going to say um, draw the whatchamacallit for the hypochlorite ion because you're actually being tested on whether or not you can do the Lewis structure and not name the ion. But I just wanted to remind you that that's what that ion was from way, way back. So, all right. So, what about this compound? What ion is that? That's the ammonium ion. Don't worry about that past this, but that's what that ion is. It's a polyatomic ion. Okay. So, we're going to draw a skeleton structure. And then we've got one nitrogen and we bring 5 electrons. We've got 4 hydrogen, that we bring one. And then over in the entire molecule, we've got a charge of plus is 1. So we have to account for the positive charge. Right here? Oh, yeah, thanks. Thank you, thank you, thank you. So we've got 9 so far. And so now for positive charge, we need to do add or subtract an electron. Subtract, absolutely. Uh-oh. I subtracted the answer. All right. So therefore, we've got 8 electrons to distribute, and they pretty much are already distributed, right? Because we have to account for what's already in the bonds. 2, 4, 6, 8. Is everything happy? Nitrogen has 8 electrons around it. 2, 4, 6, 8. 2, 4, 6, 8. Hydrogen only wants 2, and it's got 2 in every case. 2, 2, 2, and 2. Okay? So those are situations where we have ions and what we need to do with the charge. Now, there's going to be situations where when we draw a Lewis structure for something, based on where we form the double bond, it can have an identical equivalent. And don't let me get into the words. Let me just draw it and show you first, and then we'll talk about it as I explain it. So this is what we call resonance structures. But first, before we define them, I'm going to show you the example. Let us draw the Lewis structure for the NO3 ion. Okay, so I'm going to first give it some basic connectivity. Draw a skeleton, basically, is what I'm saying. Got 1 nitrogen. It has 5 electrons total. We've got 3 oxygens. They have 6 electrons total. And we've got a negative charge. So that adds 1 electron, right? So therefore, we've got 24 electrons to distribute. So how many are tied up in bonds? So therefore, we've got 18 left to distribute. So let's do that. 2, 4, 6, 8, 10, 12, 14, 16, 18. Is that it? Nitrogen needs something else, right? Nitrogen is not happy. So therefore, we need to take a pair of electrons and move it to where it can share, move it from oxygen to share with nitrogen. But if you look at these, how do we know which one? Because they look identical, right? In each case, you've got a nitrogen bonded to an oxygen that has 6 electrons. So do we take it from here? Do we take it from here? Or do we take it from here? So this is what we call a case of what we see in nature actually happens to be an average. So for a resonance structure, when we do this, when we actually draw double bonds, we can do it in each of the 3 positions, and the actual structure is an average of all 3. So let me show you that. So, so this is the resonance structure. So this is our structure. But we also equivalently, just the same way, could have moved it from this pair. Okay, my dot, we're getting out of control. And end up with a double bond on that side. Okay. And lastly, we can have a double bond at the bottom. So this is what we call resonance. Yes, we do. Thank you. Definitely do. I'm trying to get ahead of myself here. So we can have a double bond in either of those 3 positions. So if you are asked to draw a Lewis structure when you can have more than one way to represent um, a connectivity between 2 atoms that would be equivalent, then you have a situation of resonance. So basically, to, to accurately represent the Lewis structure for resonance, you have to draw all 3 and show these little arrows and say that they're equivalent. Because technically, I don't know if this is too far or not. Maybe it is. Well, let's do it anyway, just to see if it'll help. But technically, since it's an average of all 3, the electrons are pretty much just shared, um, they're kind of pooled, I guess, averaged between the 3 atoms. There's another. Mm-hmm. So let's look at the number that makes our moon. And this one still has a negative. Don't forget the negative. You have to remind me of that. So let's look at O3, ozone. And the only reason I'm naming these compounds is just this is chemistry class, and I'm just naming the compounds. But um, I'm accustomed to it. So, but we're just interested in what O3 looks like bonded together, okay? All right, everybody have that written down? O3. All right, so I'm going to go through this fast because we already know we have three oxygens. They each have 6 electrons. When we draw a skeletal structure, we got three oxygens connected together. There's no charge. So we just use up 4 of our electrons and bonds. And now we have 14 electrons remaining to distribute over the atom. We do it to the outside atoms first and do the central atom last. 2, 4, 6, 8, 10, 12, 14. The outside atoms are happy. Inside atom is not. So because we know that, we can move a pair of electrons from one of the oxygens to make everything happy. We know we can form a double bond. But the central atom is equally connected to identical oxygens that look just alike on either side. So how do we know which one to pull the electrons from? So once again, you've got a situation where it's a condition of resonance. Okay, so you have to show both of them. You can pull it from this one, form the double bond there, or you can pull the electrons from this oxygen, just pick a pair, and form the double bond on the other side instead. And in each case, we have an octet. We have 8 electrons around every single atom. So these would be the two resonance structures for um, ozone, O3. So I've been giving you, up to this point, I've been giving you atoms that we can kind of easily predict what their connectivity should look like. You just connect 3 atoms to an nitrogen. But how do you know that our skeletal structure, what it's supposed to look like this for the upper molecule? Well, we say we're the most electronegative in the middle, but there are other ways. Sometimes you can't really distinguish. There's going to be more than one viable um, Lewis structure for in molecule. So we can evaluate that molecule by assigning formal charge to each of the atoms. Okay, so we're going to come back to this concept of resonance in a little practice or whatever. We're going to kind of combine these two together and then more complex there. And let's try not to speed up. So I just go at this pace. Okay, let's look at the concept of formal charge. So formal charge, it evaluates, the charge on the atom, is based on the number of valence electrons, right? The charge on the atom we can determine from its valence electron situation for the main group elements. But the formal charge asks us to say, okay, how many electrons does this atom bring to the molecule? And how many does it actually share or possess while it's in the molecule? So how much did it have before it got bonded? How much electron density it had before it got bonded versus how much electron density it has after it's bound. So we have an equation for this. At first, we're going to use the equation slowly, But once you start to practice on it, you'll be able to do it in your head. So formal charge and um, number of valence electrons in the free atom before it got bound. And I just abbreviate this V. Okay, that is formal charge. Fc is equal to this. Minus the sum of. It looks like it's about to get complicated, but it's not. The number of non-bonding electrons in the molecule after it's been bonded. After it's been bonded, how many non-bonded electrons does it have on it? Plus 1/2 of the number of bonding electrons in the atom. So we can call that NBE, NBE. So formal charge, Fc, equals valence electrons minus non-bonding electrons plus 1/2 of bonding electrons. So let's calculate the formal charge on something. Let's see which one do I want to do. Right. We'll do the example they gave in the book. So when we calculate formal charge for a molecule, we're calculating it on each atom. Okay. I'm going to redraw this, going to put it right up here. So I can write numbers under here. So the formal charge, in this case of hydrogen, how many valence electrons does hydrogen have on the periodic table? When we were drawing Lewis structures, we know that hydrogen brings what? 1 electron. All right. So now, for the rest of these numbers, we look inside the bonded molecule. Do I need to slow down? Is everybody trying to catch up with me? Okay. So, well, we have to calculate the formal charge of hydrogen first. And then we're going to calculate the formal charge for every atom in the molecule. So the first one that we're going to do is, this is our molecule right here. So the first atom that we're going to calculate formal charge for is going to be hydrogen. So for hydrogen, that's why I have it in parentheses here. This is the element that we're calculating the formal charge for. All right. So it brings how many valence electrons? 1. And then inside the molecule, how many non-bonding electrons? Do you have any dots around it? Non-bonding electron pairs? No. So that number is 0. And now for bonding electrons, how many bonding electrons do we have around hydrogen? 2, right? So technically, so if you wanted to distribute it out, you get 1 minus 0 plus 1. So the formal charge on hydrogen is 0. So basically, it doesn't have any more or any less electrons in this bond that are associated with it than it brought into the molecule. Okay, so it has the same number of electrons in the bond that it had when it came into the bond. So now, let's look at the formal charge for chlorine. So chlorine has how many valence electrons in the free atom? 7. Non-bonding electrons around the fluorine atom. Um, Bonding electrons. So basically, this is the same thing as saying 7 minus 6 plus 1, which is 7, which is 0. This page might jump down. Don't freak out if it does. If it did, we're going to go back up. So total charge on fluorine is 0. So that's how you calculate it. But what does it mean? So what we would like to have, the atoms, the molecules that are most stable, our preferred configuration for a molecule is one that has all of the atoms with a 0 formal charge. If that cannot be, we want to minimize the amount of formal charge in the molecule as much as possible. Okay. Whatever the charge on your molecule is, I'm going to write these down so you can write them with me. I'll make sure you have them in a neutral molecule. The sum of all formal charges is 0. In an ion, the sum of all formal charges should equal the charge on the atom, on the molecule, on the ion. On the ion. Which one? Oh, it says is. It does look like infinity, doesn't it? It's 0. I was writing fast. Okay. In an ion, the sum of all formal charge is equal to the charge on the ion. Okay. We like small or 0 formal charges more than large ones. Hmm. We like small or 0 formal charges more than large ones or large formal charges. This one says when formal charge cannot be avoided, the formal charge should reside with the gas, magnitude, or When formal charge cannot be avoided, right? When you absolutely cannot find a configuration where you have zero formal charges, the negative formal charge can reside with the most negative atom. Either one. This is one of those places where heading outside. When formal charge cannot be avoided, the negative formal charge should reside on the most negative atom. That means that in this next example, that means if you don't have a formal charge, if you have three different structures and you've got one where oxygen is shows a formal charge of +1, and one that shows hydrogen a formal charge of -1, you know that doesn't make any sense. So we would pick the structure that has the negative formal charge with something that's more negative, more electronegative, like oxygen. So we would pick the structure that has the more negative charge on the more negative element. When we actually draw on the structure, we actually have two very valuable options for what is it called HCA. So which structure is this? So if you go through the formula and you calculate the formal charge, you really to do that? Okay. Alright. So okay. So formal charge for hydrogen in this one valence electron, right? It has no non-bonding electrons, hydrogen. One valence electron, 0 non-bonding electrons. It shares 1/2 of the bonded electrons here, which are 2. So basically we're saying 1 minus 1. Formal charge on hydrogen here is 0. Let me go down. I'm going to jump the page. It's going to jump. Just each element every time. I know. That's why I said once you do it a lot, you'll be able to, it'll speed up a lot more because you'll be able to say, you know, you'll be able to do the math a little bit more quickly. Formal charge of carbon. Carbon brings 4 electrons in the mix. It has no unbonded electrons. Is there a question? Okay. And carbon has 2, 4, 6, 8 electrons tied up in bonds. All right. So it's going to be 4 minus 4. So carbon also has a 0 formal charge. So now the formal charge on the nitrogen. And if you have more than one hydrogen in the molecule or something, you can do your own designation where you know which one you calculate. You can number them or whatever. If you have more than one of the same atom. But don't get it mixed up when you actually do your prediction. So formal charge on nitrogen, the nitrogen brings 5 molecules of valence from neutral free atom. It has 2 non-bonding electrons. It has 2, 4, 6, 8. I'm sorry, 2, 4, 6 electrons that are tied up in bonds. So half of 6 is 3. 2 plus 3 is 5. So you end up with 5 minus 5. The formal charge on nitrogen is 0. So this would be an awesome structure. If both of them end up being formal charges, and they could be a resonance structure. If both of them have 0, like if we did the formal charge on those 3 equivalent structures that we saw when we looked at resonance, you would have 0 each time. So those would all be good structures, and they would be resonance structures. But if they have different formal charges, then but the difference between this kind of structure and the resonance structure is that there's 2 different elements that are bound with the triple bond here. Okay. The nitrogen and the oxygen on that nitrate anion, NO3, they were all bonded to the same thing. In this case, your carbon is bonded to the hydrogen in molecule A. Sorry, your carbon is bonded to the nitrogen in molecule A. And well, you have carbon bonded to hydrogen and nitrogen. And over here, you have nitrogen bonded to hydrogen and carbon. So it's a different bonding arrangement. Looking at the central atom, it's connected to 2 separate things. But I'm not going to go through the calculations of formal charge on these, but know that they end up being 0, positive 1, positive 1, and negative 1. So we would definitely like to have a 0 charge on every atom. Much more preferably than we would the situation where we have charges on the atoms. So basically, in this case, nitrogen has less electrons in the bond than it came in with, and carbon has more. But you still see, although although it's not the ideal structure, we still see that the total formal charge is still equal to charge of the atom. Zero in this case, unless it's a cation or anion, the total formal charge must be zero. If it's a cation, the total formal charge must be the positive in the magnitude, whatever the cation value is. If it's a +2 cation, the total formal charge must be +2, etc. Okay. So let's look at one more. We're going to have one more case to predict the gas structure. And this doesn't look like to me at all. I got this out of the That's what I'm saying. I don't like this. I got this out of the book. And these are not even, they're not even correct structures. So you actually have to have two viable correct structures before you can assign a formal charge. So let's look at two different ones. Let me see if I can find another example. Okay, Dr. Jones's eyeballs struck again. I wrote the wrong thing down out of the book. The book wasn't wrong. So we're going to predict the best structure for this. All right, so of these three structures, which would be the best structure? We haven't really done one that we haven't really showed a formal charge calculation example that has formal charge actually associated with it. So I'm gonna tell you what the formal charge is on each of the others, and then we're gonna calculate one that has actually no formal charge. So this one has formal charges that are -1, 0, 0. This one has 0, 0, and -1. So now let's do the other one ourselves. Let's do the formal charge of oxygen. Oxygen brings 6 to the equation. It has 2 non-bonding electrons, and it has 6 bonding electrons. So this is going to be 3 plus 2 being 5. 6 minus 5 is equal to 1. So oxygen will have a +1 formal charge. Oxygen will have a +1 formal charge. So it's 1. So I just emphasize the fact that it's not negative. It's a +1. And so it really doesn't make sense, right, already that oxygen has positive charge on it, because we know oxygen is electron rich. Okay, the formal charge of carbon. Carbon brings 4 to the mix. And 0 non-bonding. And 1/2 of 8 is 4. So 0. So carbon has a 0. See, I told you to get faster. And then the one for nitrogen. Nitrogen brings 5 to the mix. 6 non-bonding. 2 in bonds. So, yeah. So 0. So now we've got formal charges assigned to every atom in these 3 different structures. So the last thing we're going to do, I know it's getting close to time, but we still have 4 whole minutes. We're going to use this quiz for Rose. So how do we determine which structure is the best? We don't have any that are absolutely 0 overall. Last one the best? So we said that if it has a half formal charge, we want to pick the structure that has the negative charge on the most electronegative atom. It's A. Okay, so if of all 3 structures we know that this one is the oxygen. Oxygen is much more electronegative than, we don't like to see positive charge on oxygen ever. This negative charge here is sitting on nitrogen, and we know it should probably be on oxygen because oxygen is more electronegative. Oxygen likes electrons a lot more than nitrogen. So therefore, the structure that is most stable would be the one where oxygen has that extra electron density itself. Okay, so what are our rules? Be on time for class. 5 minutes only for this quiz. No notes, no corresponding. I gave you 8 today because we were getting started. Quiz is going to be on today's lecture material. So you probably have 2 questions this time. 2 quick questions. If you missed something in class, I do post these lectures to a YouTube channel, and you can link to it from Blackboard.